right, so the classic flight control device is the control cable. Now, we've built a lot of those control cables in the general semester. However, now we're going to actually to really start to kind of put them together and kind of manipulate them and make sure that we understand exactly what they do. Believe it or not, you probably already know the majority of this information just from the control building class. But this one, we're going to kind of take it to just a little bit of a higher level. All right, so here's your control cable. We won't go too far into it. I can give you an idea. I'll put a graphic up that kind of gives you an idea of how they're set up. They're layered with a strand in the middle, and then they layer other strands all the way around. Now, any particular one wire is not necessarily that strong, but whenever you put them all together and they're twisted, and then they're further twisted into a cable itself, they're extremely strong. However, they are susceptible to a couple of things. One is, and primarily, is corrosion. That's something you want to look for them. As a aircraft cable ages and starts to break down, it will start to fray, just like a braided hose will start to fray. And so if you have it off the aircraft, one of the best things to do is just grab the whole length of the cable and just do like this. You can kind of, you'll see if there's a popped cable, it'll pop out. All right, go that way and kind of like flip it over and do like that. As you do this, you want to watch your hands because they're like needles that go into you. If it's on the aircraft and it's set like this, all you really want to do is take a shop towel and just glance over the top of it with a shop towel. Now, what that will do is that if there's a strand that's popped out, it will catch, and you'll know that, hey, look, that's bad. Now, depending on the situation, you can look up the minimums for per the AMM. What sort of damage is allowed on that control cable. It'll probably be in the same chapter as the rest of the flight control stuff. And so it may or may not have it in there. The other way to do it is just have kind of like personal minimums, just like you would with flying. And say like, hey, look, like I'm telling you right now, like if I found a broken cable or broken strand on my aircraft, I'm going to replace the whole cable. I'm just not going to take a chance of it, because the thing is that if that aircraft is flying and you lose some sort of control over it, there's nothing you can really do. You're just basically kind of in a metal coffin, and you hope that maybe you have enough control via the engine or whatever to get it on the ground safely. But the likelihood of it is that like you're not going to make it out of that situation. Flight controls are something you just don't really want to play with. So have a really high standard for flight controls in general, especially control cables. Now, these things generally don't break. I'm sure there's probably been a crash that is a result of a broken cable. But proper maintenance and having the right tension set will let you know. If you end up getting in a plane or you're annualing a plane or whatever, and you notice that like the trim is set really high one way, the control cables are probably off. They're either probably too tight or too loose, and the pilot's trying to compensate for that by trimming it out and stretching the cable in one way or the other. And so you want to like think about that and think like, okay, I see that. It's something to investigate. But yeah, control cables. The cable stops are not something that you generally see that much of. They do exist. You'll see them in some places. Usually you're going to end up seeing it kind of like hang off of another connector of some variety. And there's just like little bitty balls. We'll put a graphic up from the 8083 that kind of gives you an idea what they look like. They're not that common. Most of the time they have a swedged end fitting that will be the end of your cable. So that way, if it comes loose, that ball will catch on a cable guide and not let that cable come totally loose. You might lose some control, but you won't lose all control. So then that's better. Something that's better than nothing. But yeah, that is a cable stop. Okay, let's talk about cable connectors. We've already covered a lot of this in general, so we're not going to belabor the point, but we are going to kind of check the block for this video because it's in the ACS. So you have your control cable, you have your eye splice, right? So you'll thread this guy on. You're going to take it and you'll take your cable and go over the top, if we can make this fit. And then once you get it set up like so, then you'll just turn around and you'll crimp it down, and then it's a Nico press eye splice that you can set up. And that's one type of cable end. The other types of cable ends are a lot more common, are your swedged end fittings and your turnbuckles, right? So turnbuckles are pretty cool. You'll end up attaching this to something. The cable, let's say, will come out the other end on a swedge fitting, and then you can turn around and crank this to adjust the cable tension as needed. Like I said, we're not going to belabor this, but these are things that you want to pay attention to. This class is more kind of geared towards inspection. So the things with a lot of these things that you want to inspect is mainly corrosion is the big thing. You have a lot of like little places where the cable is wrapped around, and it's not obvious to you just looking at it that it might be corroded or damaged. And so you really want to take a lot of care whenever you're inspecting something like this, and make sure that there's not corrosion or damage hiding somewhere inside of it. You'll also want to lubricate it as per the AMM. It'll call it out and say, hey, look, put on your chapter 5, I believe it is. It'll say like put the LPS2 on all your turnbuckles or hinges and things like that. So you definitely want to make sure that it stays lubricated. The lubrication will keep the water off, and CLP is a clean lubricant protects. It's protecting it from corrosion. It's getting all the dirt off of it or anything that might cause some sort of differential metal corrosion on it. And so definitely pay a lot of attention to these little guys like this, because that's where a lot of the damage will end up hiding. Most of the time, if the cable breaks or is breaking, it's pretty easy and obvious to see. The things that you're going to miss as a mechanic are going to be in like these little bitty corners and areas that would otherwise not be that obvious, to the naked eye. Like things that people just pop a panel up there and look and see, they're going to get caught really fast. The ones that are going to cause a crash are going to be like some kind of like little niche nook somewhere. So be really meticulous and have like a super duper high standard of anything that you do. People, like, this is a thing that me and my wife get into all the time. She says that my standards are too high and I expect everybody else to live up to them. That's rooted in doing this kind of work, that if it says like clean this compartment, well, my level of cleanness is always going to be like an order of magnitude higher than the normal. And that's because what you want to do is always exceed the minimum standard, so that way you know that you did a good job, and that there's just the very little possibility of you missing anything. And that's absolutely true with control cables, because this is a no-fail mission. If you screw up a control cable or screw up a flight control, it's very likely that you'll get somebody killed. So always follow the manual, make sure everything's rigged right to the TCDS, which we'll get to in a little bit, and make sure that everything is by the book, because that's how you keep people safe. Okay, cable guides will come in a variety of different shapes, form, and fashions. We'll put a graphic up of the 8083 where you can see it. Here's a real life example of one. This is going to be a throttle cable for the engine that used to be on the Beach 18. You notice that you have a guide that attaches to a metal standoff that makes sure that throttle cable is routed correctly, and then it goes through a pass through here in the fuselage, or in the firewall, so that way that throttle guide or that throttle cable doesn't rub on anything. Now you'll get a lot of the same thing in control cables as well. Now, cable guides are something that you want to pay attention to. Now, most cable guides, the vast majority of them, they're there to keep the cable from touching anything else. Sometimes they come in the contact table, but by design, they're usually not meant to sit there and ride on it. If the cable is riding on it, you need to start checking alignment. You need to start checking, making sure that it's under the right tension. Because if it's under the wrong tension, it's going to slack down, or maybe like get brought up and touch something that's not supposed to. If it's out of alignment, then you've got a pulley somewhere that's not set right, and that could run to a situation where, under the right conditions, that cable pop off that pulley or break something or break itself. And so the cable guides are usually really good, kind of like canaries in the coal mine, to let you know that there's something going on, something wrong. So you might want to look at that. What do we have to do to maintain, once we've taken all the components and put them together, what do we have to do to maintain your control cables? What does it look like whenever we get to an annual inspection? What are we doing? All right, so there's two things we're really looking for on any aircraft, on any control cable system, there's like two kind of themes here. First off is like the classic condition and security, just doing general visual inspection, making sure that nothing is obviously wrong for it and that there's no corrosion. Corrosion being the biggie. A good way to inspect these cables simply just by running a shop towel down there. You just run the shop towel down the length of the wire. If it's connected to the aircraft, it'll hang that shop towel, and you'll know that there's a strand that's missing. And usually, if a strand is popped on a control cable, that means a new control cable. But the maintenance manual will tell you what the standards are for that particular aircraft. The other one is simply just to pull it off and then start doing it like that, and you'll see the wire pop. Now, the other big thing is tension, cable tension. Cable tension, if it's too tight, you're going to overstress that cable, and it might push it into a realm where it could potentially fail. If it's too low, like it was with my aircraft when I first got it, you stand on the rudder, and you barely got any play on the nose whenever you put those control inputs in, because the cable tension was too low. And now, why does the cable tension get too low? Well, so whenever you get hot environments, it's going to want to or expand. The metal does, and as the metal expands, it starts to slacken like so. But if it gets cold, it might be super duper tight. So it's really important that it's checked on the annual, that you do cable checks on every single one, make sure that it doesn't need to be adjusted. And it's important that you make sure that you put that cable about mid-range. So if it can be between like 40 to 50 pounds on the cable, you want to make sure that whenever you pull it, it's about 45. The reason being is that you don't know what's going to come up, where that aircraft is going to go. The owner might say, "Oh, I'll only ever fly locally," or whatever. But you never know where, like, Aunt Sally dies and I have to fly up to Alaska. Well, he's going to get in his plane and go up to Alaska, and it's going to be a lot colder there. So if you have that thing already at the stops at the 50-inch pound mark, that's where you rigged it, or 50-pound mark where you rigged it, and it flies up to the very tip top of Alaska where it's super duper cold. All of a sudden that cable's getting really tight, and let's say he gets into some choppy air while he's flying around up there and decides he's going to step on that pedal, and it's going to snap it, or it could potentially snap it. Doesn't necessarily mean it's going to, but either way, if you put it in that center mark on that range, it's going to allow the cable to get tight, get loose, and still be within acceptable limits, regardless of where that aircraft goes. So that's something that's really important for you to check. And then right with tension, it goes alignment, making sure that it's set up right. Because even if you have it set on the right tension, if it's out of alignment, besides just wearing on something that's not supposed to wear on, you're going to turn around and not get the full deflection of that flight control that you want. And so that guy's going to turn around and want to steer the airplane over there, and if it's not rigged correctly, it's not going to go there. It might go the wrong direction or whatever. And a lot of that can come back doesn't have the right tension, or it's just out of alignment, so he's not getting the full input that he's wanting to get. So those are the two big things. Now, another thing to keep in mind with cable tension maintenance and inspection are pulleys. Pulleys on cable systems are there not to give you any kind of mechanical advantage. Typically, it's there to just route the cable the correct way. And that's something that you're going to encounter a lot, especially on GA aircraft. If you're inspecting them, you're going to want to go up there and spin that pulley, and you're looking for two things on a pulley. One is the bearing okay, and you'll be able to feel it. Like if it spins smooth, then that's good. It's fine. It's exactly the way it's supposed to be. You'll shoot some LPS2 on it, keep it lubricated, and go on to the next one. If it starts to catch, and like this is with any bearing that we come across, if you feel like a tit, like it's starting to stutter or whatever, that means that there's probably something inside of that bearing, or the bearing is starting to just fall apart on the inside, and it's causing it's wanting to roll, but then there's something hanging, and it's giving you that intermittent that feel to it. And you'll start to develop a feeling for these things as you start to play around with them. You feel what a good bearing feels like. Oh, okay, yeah, the pulley's just supposed to spin like a fidget spinner, but then whenever you get one that's bad, it'll go to spin and then stop, and then you can just barely push it, and it'll roll over the top, whatever's stopping it, and it'll start to spin, then it'll stop. You'll do that over and over again. So you want to look at that. The other one is you want to look at wear marks on the pulley itself.
Now, the different wear marks that you'll see, generally speaking, will kind of indicate like, hey, look, this is out of alignment, it's over tension, it's under tension, or it's fine. Like now, every pulley that you see, they're just phenolic blocks, and phenolic all it really is a kind of glorified paper with like resin that's hardened up. And so it's going to leave a certain impression to it. Almost every single pulley that's been in service for more than a year is going to have like kind of like the outline of the cable laying on it. That's not that big of a deal. It's whenever it gets like really excessive, or you start to see like a very specific wear pattern that you can recognize and say like that, there's something going on here because of this. One side of the pulley is wore out, whereas the other side of the pulley doesn't seem to be that way. It means it's out of alignment. If it's really deep into the pulley itself, it's over tension and needs to be relaxed, and that pulley probably needs to be replaced. There's different wear marks you'll see that in a general sense you can kind of start to forecast like what's going on in that system, but every aircraft and every situation is fundamentally unique. So you just need to know that like this is what a pulley looks like whenever it's right, when it's good, and then this is what a pulley looks like whenever it's bad, and then know when to change it. Other than that, cable maintenance generally on the whole is pretty solid. It was used for a long time. It's still being used today. If you get a new, they're not in production anymore. I think they still use them for the P8, but the 737 NGs, which just got replaced by the Max like not too long ago, finally, like Westline and Renton went away from them. They were still, even the Max, now I think about it, like they still use cable tension systems in there, and they're perfectly reliable. They're great. They don't generally, as long as you maintain them correctly, you don't have to really worry about them too much. And then even if you have a complete electrical failure, like say if you get like Airbus A320, it goes out, the cable is still there in a 737 to fly the aircraft with. So they're actually a lot safer than a lot of the more modern systems that are using hydraulic pressure and electrical signals to do the fly-by-wire thing. And so these are great systems, and they're super, super reliable, and they just have to be maintained, which is what you're there for. All right, so there's some aircraft that do not use control cables. Rather, they would use push-pull tubes or torque tubes or bell cranks. What is a bell crank? What is a torque tube? What's a push-pull tube? And what do we owe it in terms of maintenance? All right, this is where you're going to start to see a big differentiator between general aviation aircraft, smaller aircraft, and bigger aircraft. And the divide really kind of comes into being somewhere in the business aviation world in terms of scale. So out of all the heavy commercial aircraft that you may find out there, most all of your heavy commercial aircraft, at least all the ones made by Boeing, they're always going to have push-pull tubes somewhere, and they're usually going to be fly-by-wire and not hydraulically actuated. Meaning that like the control wheel, you're going to put your yoke, you're going to put control inputs in, or on your pedals or whatever. That's going to turn into an electrical signal that's going to go to a hydraulic actuator somewhere that's going to move a push-pull tube, typically. Now, we talked about the 737 is a little bit different. Your Embraers are going to have, depending on which model Embraer, are going to have control cables. I don't think there's a single Airbus aircraft out there that has control cables. Most all of them are going to be push-pull tubes via hydraulics, via fly-by-wire situations or systems. So what will end up happening with the push-pull tube is it's very, very simple. It is a connecting rod. That's all there is to it. It has an advantage over cables because we were talking about cable tension will slack or get lighter. The tube is solid, or well, it's not solid, so they use a hollow tube of aluminum. Now, the way they typically work is that, let's say it's connected, let's say you're in an OH-58, all right, a Bell 206 helicopter. You're going to push forward on the collective, and when that pushes forward, it's going to go into a series of bell cranks or intermixing flight controls that then pushes on a tube that then goes all the way up a broom closet that then pushes on other bell cranks that either go directly to the swash plate that causes the controls to move, the actual flight controls to move, in that case the blades to move, or it's going to go to a hydraulic actuator that gives a mechanical advantage to that small movement that then goes up to the swash plate and causes it to move. So generally speaking, it will always go control input, push-pull tube to the actual flight control surface itself. So this is how they typically will end up working. You'll end up having the pilot, who will then actually put a flight control movement in, however it works, into a push-pull tube, and then it will connect directly to a flight control surface. Now, in between here, that push-pull tube might encounter bell cranks, intermixing flight control devices that allow for other control inputs to be put in, or it might go to a hydraulic actuator. It might go to a computer of some variety, but then it allows different things to happen, or different detections, or anyways, yeah. So now it's pretty straightforward. If I have, let's say that's a push-pull tube, and I push on this side, on the right side, I'm going to push it. What happens to my other finger? All right. There is no lag. There is no any sort of adjustment that needs to be made once it's originally installed. It's not going to get shorter. It's not going to get longer. That's it. Now, it does have a disadvantage that sometimes in certain flight configurations, the power or the weight that could be on a said flight control would be extremely difficult to overcome with just your own human strength, which is why we use hydraulics a lot of times to supplement that power. But that being said, at the end of the day, it still relies on you to push it forward. Now, where this kind of came into play is that the first 737 MAX crash, one of the things that came out is like, well, they could have just pulled out of the dive. Well, the amount of weight that was actually on that yoke at the time would consist of you having to sit down in a chair and then pull 200 some odd pounds to your chest that way. And most people can't do that. And so the idea of being able to pull that weight was, kind of not really realistic. But that's kind of the disadvantage, that there's so much actual control input being placed on the push-pull tube that trying to overcome it can be somewhat of a challenge if you don't have hydraulic assist. Now, I saw this all the time in the OH-58. If we had a hydraulic failure, it was like losing power steering in your car. And if you've ever done that, you could still turn the wheels, but it would be very, very difficult without hydraulics. The same thing with flying around. Especially with a helicopter, you're relying on very precise control inputs to get the helicopter to do what you want it to do. Whenever your hydraulics is applied, it's really easy. I've literally watched people fly with a pencil. So you have the yoke or the collective, the cyclic, set it up like this, and they would take a pencil and they'd push on it and they would fly the helicopter with a pencil. And they're kind of demonstrating how precise you have to be to fly the helicopter, and that just little movements make a big difference. Whenever you lose the hydraulics, in order to make the flight controls move at all, you have to put big movements in. So you're trying to make big movements to make the helicopter fly very, very precisely. And so that's the role hydraulics will end up playing in this. But it all gets communicated over push-pull tubes. And so now those push-pull tubes have a couple of different components that we'll kind of look at. All right, so one of the things that you will encounter with push-pull tubes is bell cranks. You can also see them in control cable setups, though they're less common. Usually they'll just use a pulley. Now, push-pull tubes or bell cranks, what ends up happening, this is for the flaps out on the Cherokee. You'll have one tube that will come in and attach in some direction, all right? And then as it makes its movement, it then changes directions totally into another push-pull tube. So on the Cherokee, you'll have a clevis that attaches here that goes to the flaps. So whenever you pull up on the flap handle, it causes this to rotate, and then that pulls the flaps down or pushes them into position as needed. Now, these are really, really common, and you'll see them all over any type of aircraft, and they are all they're fundamentally unique. And so every aircraft is going to have a set of these that if they use push-pull tubes, they go all over the place. And one of the challenges is that if ever one of these gets damaged, you'll run into supply chain issues usually pretty quickly, because there's not that many of them out there. They generally don't go bad, but you could end up having one damaged in a bird strike or something like that. or whatever. Or you could have corrosion. There's also bushings that go in here. So I don't know if you can see it on the camera or not, but there's the inner race of a circle, and that's just a bushing that goes in, that slides into the actual metal piece. What happens is these get CNC'd out, and then you just have this thing, and then they'll press bushings in that then the bolt goes into, and allows that bolt to move without creating a lot of problems. On that note, they typically will end up having if corrosion is ever in here, it's always going to be like right there in those areas. Generally speaking, the outside will be zinc chromated, and that never really scratches them or anything else like that. So they're generally pretty good. Where you'll end up having your problem is right here, and you'll start to see that. If you start seeing a lot of that gray, goopy, metallic, degenerative stuff come out, that's usually an indicator that at the next service, that bolt needs to come out and get inspected. That bushing needs to come out and get inspected and make sure it's not falling apart. Now, you wouldn't think it, but just a little bit of play in this can be felt in the controls, especially under like high pressure hydraulic systems. A little bit of play goes a long way when it comes to flight controls, and it can make a big difference when you're flying. If you're trying to be really precise and come in and land, let's say like you're trying to stay under the clouds at this ILS or whatever else, you might need just that little, half a centimeter of play inside of the bell crank to be out, or else you're going to be off one way or the other. You're going to over control or whatever. So have a pretty high standard for these parts, because like a little bit goes a long ways, especially with this kind of stuff. But that's the bell crank. All it really does, all you have to really remember with bell cranks is that like as it changes position one way, it changes the position in another way. It's just basically how do you navigate angles and weird aircraft structure places to get your flight control input. Another thing it can also do is it can take multiple inputs, or outputs. So you could have the bell crank here and have something attached all the way up, so that way whenever this one control input comes on, it does a whole litany of things on the other side. Or it could go the other way. So like on the 58, there was we call it the intermixing bell crank. It was basically tied all the flight controls together in one spot, so that way if you made a control input one place, it would cause you to have to adjust for it somewhere else. And the reason being is that, when we'll get to this here, this class, is that if you pull power on a helicopter, it wants to rotate. So you have to then put your pedal in to keep it going straight. But when you do that, it causes things that happen with the cyclic and so on and so forth. So you're back to needing more power or less power or whatever. But the intermixing bell crank helps to mesh all that together, so the pilot's not constantly doing like this the whole time, rather than just making smaller adjustments. And that's the power of bell cranks. So you can think through the way the system works and build it out perfectly on the front end. It makes the pilot's job a lot easier. Okay, so let's talk about torque tubes. Torque tubes are like this. This is out of the Cherokee, just the flap actuator tube. I'm not sure what the technical nomenclature for it is, but effectively it's a torque tube. All a torque tube is, if you look at it, it's just like a push-pull tube, except for instead of pushing and pulling, it torques, it twists. Now, on the Cherokee, it's really, really simple. Like whenever you pull the flap handle one way, it just torques one way or the other. Real low speed, low amount of torque, very, very simple. However, torque tubes are used extensively on heavy commercial aircraft for any number of things, but primarily on a 737, it's used to lower the flaps. Now, except for in this situation, it's not just a one click or two click kind of thing. It actually spins a lot, and they can be extremely dangerous. If you get your hand or clothing or glove caught up in there, it'll pull you up in there and pull your arm off or your hands off or anything else. So something to be very, very careful around. We're gonna watch a video right fast, and I'll do a voiceover narration to kind of show you what a torque tube looks like and where it's at. And you'll get very clear, you'll understand, it'll be apparent that you don't want to put your hand on that while it's spinning. All right, it's a 737 flap transmission that's in action. The tube that we want to pay attention to is in the top right-hand corner, that's denoted by that yellow or orange and black tape. And you notice what the torque tube does is that as it spins perpetually, that's working out, or that's going out to the flaps
and then is lowering the flaps incrementally as needed, as you see here. So notice that the torque tube spins. It goes into a series of well, they're not bell cranks, but they're transmissions, and then on the bottom, that jack screw actually pushes the flaps the way that they need to go, and that is how a torque tube operates. But notice, it's just the thing to take away is that it just spins at a higher rate, now, or at a low rate. It just it takes the inputs from the cockpit, it turns into a torque action that then is then converted to some sort of linear action somewhere on the aircraft elsewhere. Most commonly, you're going to see this in the flat track, but it could be in any number of other places depending on the design of the aircraft. But that's a torque tube.
Now, the dynamics that are at play with flight controls can lead to some unique situations, such as flutter or being a flight control being out of balance, say because it got painted or whatnot. So, what do we need to know about that?
Okay, so this is what a fluttering flight control looks like. The elevator on this plane has just gotten away from the designer, mechanic, pilot, whoever, and it's starting to oscillate uncontrollably. Okay, so flutter by definition is a rapid and uncontrolled oscillation of a flight control surface on an aircraft that is caused by a dynamically unbalanced condition. Now, you can think about this if you're familiar with pulling a trailer. Let's say you were to put a lot of the weight of the trailer on the very end, behind the axle, and all of a sudden you jerk the steering wheel as you go down the highway at 70, 80 miles an hour. And as that trailer starts to come back and forth, reacting to your control inputs, it just starts to jerk uncontrollably one way or the other. And then as it goes back one way, it makes the action-reaction even worse coming back the other way until eventually something has to give. It can't just keep on building on itself that way. And so in that metaphor, what ends up happening is it rolls the vehicle or snaps the trailer or crashes in some way, shape, form, or fashion. Now, with a flight control surface, what will eventually happen is that this aircraft will lose its vertical or its horizontal stabilizer. It'll just break off and be gone, and the airplane will crash. So, in the design phase of an aircraft, this is one of the things that they try to make sure can't happen. They make sure the flight control is set up in a way that flutter just won't happen, and then they test for it during flight test. Like, it was one of the biggest tests they do is just like a flutter test, and they try to induce flutter as much as they possibly can in a controlled test procedure to see at what point will the flight controls begin to flutter on a certain aircraft, and then they will back engineer that, like, and say, like, okay, well, don't operate it in at this airspeed in this way, so on and so forth, to try to keep the pilot from inducing a fluttering or characteristic into the plane. And then they'll also go back to and redesign things that they think might help reduce the amount of flutter. And then on maintenance, it will say, like, hey, look, here are the procedures for making sure that the flight control is balanced appropriately, and if it's not balanced appropriately, then this is what could happen. You could cause flutter.
So as maintainers, our job is to make sure that the flight controls stay in the balanced position that it was delivered in whenever it was first manufactured. That means that anytime we paint a flight control, we need to rebalance it because we've probably applied paint a little bit more heavily on one side or the other, and could cause a flutter situation to be induced. It also means that anytime that we work on a flight control, if it comes off the aircraft, gets modified in any way, shape, form, or fashion, and then put back on, it likely needs to be rebalanced. Now, this is an overview because the flight control balancing procedures are unique to every single aircraft, and so you need to make sure that you follow the aircraft maintenance manual to make sure that the flight controls are balanced when they're required to be balanced and in the way that they are required to be balanced, so that way the aircraft maintains its flight characteristics as it was designed and is denoted in the TCDS.
Okay, so static balance is the tendency of an object to remain a station is remain stationary when it's supported from its own CG. Meaning that if you have, like, think of a seesaw. If a seesaw is perfectly balanced and you put it there where it's nice and horizontal, if it's balanced, it will just stay there, right? Now, if you put it out of balance, it'll go in the direction that it's, the out of balance characteristic takes it. But if it's perfectly balanced, you should be able to just place it anywhere, and it will just stay there, nice and static, or nice and stationary. Now, when a control surface is mounted to a balance stand, a downward travel of the trailing edge below the horizontal position indicates it's under balance. Meaning, all right, if you look at the graphic there, if you imagine the leading edge is where the flight control attaches, which is true of most flight controls, or pretty much all flight controls now I think about it. If you were to set it on there and then it starts to fall down, it's under balance, meaning the trailing edge is wanting to take over and pull it down, all right? Now, some manufacturers indicate this condition with a plus sign, and an upward movement of the trailing edge above the horizontal position indicates an overbalance, and it's designated by a minus sign. Now, these signs show the need for more or less weight in the correct area to achieve a balanced control surface. Now, a tail-heavy condition, which is a static underbalance, causes undesirable flight performances and is not usually allowed. Better flight operations are gained by a nose-heavy static overbalance, and most manufacturers advocate for the existence of a nose-heavy control surface, meaning that it wants to dive on you.
Okay, so let's talk about like underbalance and overbalance. Let's say you have an airplane that's flying along, so you have a grand old time, right? And you have an underbalance, right? It means that it wants to pitch down like that. The trailing edge wants to come up, wants to push the nose down, and goes down like that. We want that. Why? Because if the airplane is flying along and you have it, say it's overbalanced, so it wants to come up like so, and then something were to happen, and then the natural tendency of the airplane is to pitch up like this. This is how you stall an aircraft. It'll go up, it'll stall, it'll kick over, probably go into a spin, crash, kill everybody, right? If it's underbalanced as it's flying along and something were to happen and it would nose down, the airplane is still going to want to fly, because what will end up happening is it'll nose down, it'll pick up some airspeed, and it'll want to climb, and then it'll kind of get to where it bleeds that airspeed off. As it bleeds the airspeed off, it'll want to nose back over, and it'll just keep porpoising like that, and it gives you a lot more time to recover from that condition, or to wake up, or whatever the thing that caused it, rather than just going like boom, dead almost immediately. And so that's true with everything, to include balancing of flight controls. Now, a flutter in the flight controls is going to be caused from a out of balance condition, where it's going to want to make the flight controls flutter like that. Eventually, that almost always results in a structural catastrophe. It basically breaks off and falls apart. And that's why flutter is so bad. It's the one thing that it's just it absolutely cannot happen, because once it starts, it's almost impossible to get stopped. And then the only way that it's going to get stopped is that it flutters so much that it basically rips itself off the stops, and you crash the airplane and you die. Now, you generally don't see airplanes going down over flutter because it's so well engineered out of the airframes. Now, back in like the 40s and stuff like that, whenever we were starting to learn this stuff, it was a more common thing. But nowadays, most aircraft that were prone to flutter have naturally selected out of the pool of potential flyers. And everything else has been basically fixed at this point. But it's still good to know, especially the one place where this comes into an aircraft mechanic's life in 2025 is whenever you're painting flight controls. That's whenever you have to really be worried about balancing flight controls again. Now, there's other conditions, and the maintenance manager call this out, like, hey, look, if you do this, you have to rebalance flight controls. However, paint is the one where it really will get you in trouble. So you always, if you're going to paint flight controls, it's fine. Pull them off, strip all the paint off, repaint them, and then you have to balance them and make sure they balance perfectly before you put them back on. Because the next step is you're going to have to rig it. If you have an airplane that's perfectly in rig, but the flight controls are out of balance, it's going to send you chasing your tail, because you're going to get up to flying. It's going to be doing all this kind of crazy stuff, and you're going to be like, what's going on? You can fly back down. You want to re-rig the plane or check the rig on. I don't understand. And the whole time is because you're chasing a out of balance flight control, if it doesn't kill you in the process. So that's flutter and flight control balancing.
All right, now that we have a pretty firm grasp on all the components of a flight control system and what a flight control systems are and how they work, what do we have to know and to do to rig an aircraft's flight control?
Okay, checking the rig of an aircraft is going to be divided into two camps. One is structural rigging. Thing is that like you be flying along, and the airplane's always wanting to pull to the right. You can't figure out why. You land and you check all the control cables, all your flight control surfaces travel correctly. Everything is set up, and you take back off and it's still pulling to the right, and you still can't figure out why. Well, what ends up happening is that something happened to the aircraft, and it might be twisted or bent in some way, shape, form, or fashion. Something's out of rig structurally. And so one of the first things you do just to eliminate that as a possibility is a series of structural rig checks to make sure that the plane is still built correctly and it's not warped or twisted or off kilter or something else like that, causing the airplane to have this weird flight characteristic. I was contacted by a airplane owner 7-8 months ago with this exact problem, that like they had rigged out the airplane, but everywhere they went, they wanted to roll on them just constantly. And whenever we got the airplane down and checked it all out, one wing was sitting in the incorrect position, causing that roll to happen. So there's things that you need to check. So if you're going to do a rigging check on an aircraft, you're going to start with that. Then you're going to go to flight controls and make sure everything's rigged correctly per the TTDS and maintenance manual. All of this is to say that we're going to give you a general overview of it. None of it is going to be prescriptive to a certain aircraft. Every single aircraft has its own procedures, its own process, its own numbers, everything. And so you always want to make sure that your aircraft matches the maintenance manual they're using and its effectivity code. I just got off the phone this morning with a gentleman that has a Cherokee 140, and he's asking a lot of these Cherokee 140 questions. And what I don't think he realizes that like the Cherokee 140 is like almost like a family of airplanes rather than a specific airplane, because there have been so many changes done to it that even inside the same manufacturing year they made changes. And so they have like all these different subvariants of the Cherokee 140, meaning that like one piece of information that's applicable to like my Cherokee 140 is not necessarily applicable to his Cherokee 140, even though they're built in the same year. So you always want to make sure that the effectivity code matches the maintenance manual, which then goes to the airplane, to make sure that you're doing all of these rigging checks correctly. If you start using the wrong information, worst case scenario, you're going to crash an airplane. Best case scenario, you're going to run around in circles and not be able to fix anything and not know why. It's because you had the wrong manual the entire time. If you get working in an MRO and you're doing stuff like this is something the FAA is going to spot check you on. I saw guys get in trouble one time because they had printed off a bunch of maintenance manual stuff because they did the same thing every single day. And then whenever the FAA spot checked them, they looked at their printouts, saw that it was from 7-8 months ago, and then realized that they had used that maintenance manual over and over again on different 737s with different effectivity codes, meaning that they had rigged things probably the wrong way because there were so many different types, variants to all those different aircraft. So make sure that you're using an up-to-date manual with the right effectivity code for that aircraft with any of this. That being said, let's talk about structural rigging.
All right. So the 8083's definition for structural rigging is the position or angle of the main structural components as related to the longitudinal datum line parallel to the aircraft center line and a lateral datum line parallel to a line joining the wingtips. Before checking the position or angle of the main components, the aircraft must be jacked and leveled. Okay, so what does that mean? So first off, what is the longitudinal datum line? So that's the center line of the aircraft. You should be able to draw a line from nose to tail, and it should be in a straight line. And then of course, the horizontal line of the aircraft, you're going from wingtip to wingtip, and that should cross the aircraft center. Now, just remember, for like weight and balance, your CG should be just a little bit forward of that imaginal line, and your center of lift should be about right there, right? And so the first thing that you're going to do is make sure that the aircraft is actually level and not sitting on the ground, because sitting on the ground could cause things to flex or give you some sort of erroneous indication. You want to make sure that the aircraft is giving a good presentation of how it actually flies and what it looks like. And the way we do that is we're going to jack the aircraft up at its jacking points, which will cause the wings to flex, yes, but it's going to cause the flex just like it would in flight, so that's a good thing. And you also want to make sure that it's level. It's not sitting one way or another, kind of weird. Now, the way that we do this is that most aircraft have a like a leveling plate. On this, they're going to call it a grid plate. And what you're going to do is you're looking your maintenance manual for jacking and leveling. You'll jack up based on their jack points, and you'll attach a plumb bob to whatever piece of structure it calls it out, and then you're going to hang that plumb bob right down to the grid plate. Now, if the nose is a little bit high, you're going to lower the nose jack just a little bit to cause that plumb bob to swing back aft. Same thing if the tail is high, you're going to just keep on making those little adjustments until you get the aircraft centered on there. Now, once it's centered, we're ready to start doing some checks to see if it actually meets the requirements for the maintenance manual. Which, once again, all of these aircraft are different and all the procedures are going to be different. But this is just kind of like a notional high-level overview of how to go about checking the structural rigging. All right, so now once the aircraft is jacked and leveled, there's different ways that you can check for structural alignment and rigging angles. Some people use special rigging boards that incorporate a special instrument like a spirit level or an inclinometer for determining the angle that are used on some aircraft. On a number of aircraft, the alignment is checked using a transit and plumb bob or a theodolite and siding rods. It just kind of depends on what era aircraft we're talking about and what the procedure is in the maintenance manual. Now, checking with alignment, a suitable sequence should be developed and be followed to be certain that there are checks made on all the positions specified. So they typically include wing dihedral angle, incident angle, verticality of the fin, engine alignment, symmetry check, and then horizontal stab incidence or dihedral. Now, the only time I've ever actually done this in real life is whenever we're installing a new tail boom on a helicopter. We would check and make sure that the tail boom is aligned to the helicopter, usually through a series of shims on the mounting bolts right there, and we were able to shift that one way or the other. And the reason why we did that is because it had to be within a certain gap or a certain I guess tolerance, because we ran the helicopter or the tail rotor drive shaft down that tail boom. So if it was off a little bit, it would basically you'd crank up and bad things would happen. I never saw one out of alignment crank up, but I'm sure it's nothing good. But this graphic here just kind of gives you an idea of checking the dihedral. Now, if you remember back from early day structures, the dihedral is the angle that the wing has as it departs the fuselage. The angle that it creates is what dihedral is. Now, you can use that special dihedral board with a spirit level that's incorporated, so that's a kind of a special tool just for doing this. That's often what will end up happening is that you'll have special tools for definitely the bigger, more complex aircraft have a special tools kit that you'll have to come up with. But if not, you can always use a straight edge and an adjustable level, and you get to where you know that the aircraft is level, and then you kind of adjust as needed. It really kind of comes down to whatever the maintenance manual calls out, and you just follow that. All right, so incidence. Incidence basically refers to the angle between the chord line and the ground or whatever the relative plane is. Incidence is usually checked in at least two specified positions on the surface of the wing to ensure that the wing is free from twist. A variety of incidence boards are used to check the incidence angle, and some have stops at the forward edge, which must be placed in contact with the leading edge of the wing. Others are equipped with location pegs, which fit into some specified part of the structure. The purpose in either case is to ensure the board is fitted in exactly the position intended. In most instances, the boards are kept clear of the wing contour by short extensions attached to the board. So like you can see, here's an example. So basically, the maintenance manual will tell you to produce either this tool or this set of tools. These a lot of times you have to manufacture like a wood part, and you'll set the level up to on top of these like wooden manufactured parts, and you'll run it up and down the wing at different points to see if the wing is twisted at all. Now, effectively, if the wing is level and then the level is level, they'll match up. But if you get to a point where the wing is twisted, and it wants to turn one way or the other, then you'll start to see like, oh look, the wing is warped, and then that means that the wing's basically no good. You're probably going to end up replacing it. At the very least, you'll be reworking it pretty intensely. So like you'll just run that up and down, and you'll start to see the bubble move one way or the other. This isn't too terribly different than checking like the concentricity of the shaft. The tooling is radically different. Instead of using a micrometer, you're using a level, and the level's not going to be as precise as the micrometer, but it's going to effectively tell you the same information. They're going to say, hey, look, this thing is twisted and it's going one way or the other. It's not supposed to be, but that's how that works. All right, this is how you check the verticality of the horizontal fin. It's actually pretty simple in concept, and once again, you follow whatever the maintenance manual says. But all you're really doing is you're going to measure from the tip top of the vertical fin to the horizontal stabilizer. If you don't get the same measurement on both sides, or you get a measurement that's not consistent with what it's supposed to be per the maintenance manual, you know that you have something bent somewhere, something's out of alignment. It could be the vertical fin is out of alignment. Now, a lot of these aircraft, you attach the vertical fin to the aircraft. It's not necessarily part of like the structure in a way that like that's part of the original like substructure that is built up from, rather than it's a separate device altogether, and you come and you stick it, you attach it to the plane. So whenever you attach something, there's going to be shimming and all kinds of stuff that needs to happen, and you might end up seeing that, hey, look, this plane is flying weird because the vertical fin is out of whack, and we need to check the alignment of it. And you come to find out, like, oh, yep, it is out of alignment, and now we need to make some adjustments. And that could be simply just taking the shims off, putting new shims on, or whatever, to get it to where it needs to be. Same thing with the vertical stabilizer. A lot of them, they are attached, or they're part of the flight controls just in general. You have a stabilizer where it the whole thing moves. That could be a rigging problem. It's not necessarily like a structural problem that you need to fix. But either way, this is how you go about checking that. Notionally, once again, like every aircraft is different, every maintenance manual is different. All right, lastly is engine alignment. Now, this is actually probably the most common one that you'll do, because you'll end up hanging engines. And so one of the checks that could potentially happen, depending on the type of aircraft, is to make sure that the engine's aligned correctly. Now, you wouldn't think it, but like just a half inch of being out of alignment one way or the other could have massive ramifications for the way that aircraft flies, where the exhaust goes, all kinds of things. So being in line is really important. So in this example, you have a four-engined aircraft that has gotten new engines put on it, and then you're going to end up measuring from different places to make sure that the aircraft is actually is symmetrical. So because it's also a symmetry check, but also the engines are lined up the way that they are supposed to be. And if they are lined up the way they're supposed to be, that's a known distance from different points on that engine to the fuselage. And so, like if it's off one way or the other, you can very well bet that the aircraft's not going to fly right. And even if they do manage to get it off the ground and get it flying, it's going to probably stress the aircraft in ways it wasn't certified for, and so it's going to develop all kinds of issues later on. So you definitely want to make sure you get this right. But once again, like the maintenance manual will walk you through all of these structural rigging checks if they're required at all. All right, so once we've determined that the aircraft is aligned structurally, we're ready to start actually rigging, like truly rigging the flight controls. And probably one of the most common ways that you're going to rig flight controls is simply by checking the right cable tension, ensuring that the cables are routed the correct way per the AMM, per the IPC. It'll lay out and say, like, hey, look, this is where these cables should go. And then you're going to turn around and say, okay, well, now that we know that the cables are there, are they under the correct tension? Yes or no? So this is an example of a tensiometer. There's a bunch of different kinds that are out there. This is just one of them. We have one of these style of tensiometers here, and we also have other types as well. So on this one, a riser or plunger is pressed against the cable to form an offset, meaning that riser comes up and it pushes up on the cable, and then you have the two anvils on either side that hold the cable down. And what it's measuring is like how much force does it take to push that riser up, so that way it gets a certain level of deflection, and that level of force is then indicated on the face of the tensiometer itself. So that will tell you, hey, look, it's at 35 pounds, it's at 40 pounds, 100 pounds, or however many it needs to be. Now, the other component of this tensiometer is the table on the bottom side. Now, if you'll notice, it on this example, it says riser tension in pounds. So, like 70 pounds on the riser, it means different levels of pressure depending on the cable size. All right. So, a 5 30-seconds cable is actually 70 pounds on the riser means 30 pounds of actual pressure on the cable itself. But if it's a 3/16 cable, it means that it's 42 pounds of pressure or of weight on the of tension. Excuse me. And so you have to always remember that. Make sure that first off, anytime you're using a special tool like this, you're making sure that it's calibrated and that it's in calibration whenever you do it. Number two is that you're going to use it the right way, and the way that you interpret the readings from these tensiometers in this particular type, this particular style, is taking how much pressure is being indicated on the face of it, and then using the manufacturer's data to say, like, okay, if it says 70 for this size of wire, it means actually 30 pounds, or this size of wire, it means 42, or so on and so forth. So that means that you also have to understand and be know the size of wire that is being run through that aircraft, and then your IPC will tell you if the AMM doesn't tell you explicitly whenever you go to do the task. Now, as we stated before, the other thing to take into account is the amount of tension on that flight control needs to be calibrated for the temperature that that the aircraft is sitting in. So, like, if you have a say 100-pound load, depending on the wire size, it's going to change pretty significantly whenever you go from saying like 0 degrees, which is for 100 pounds according to this chart for a 1 7/8 7x19 wire. 0 degrees has it at about 45, or let's say 50 pounds. But like if you go up to, let's say, 120 degrees, say you're in Death Valley, the same wire, same tension being indicated, it actually is going to jump up to 100 pounds. So you need to make sure that you're rigging it correctly for the ambient temperature that's there, and also keep in mind whenever you're troubleshooting any kind of like flight control issues, that if the aircraft owner came from, say, like a really cold environment to a really hot environment, or vice versa, these things are going to play a part. Now, typically, modern aircraft are going to have ways to compensate for this, if not indicate that, hey, look, the cable tension is changed or lower, or whatever, or maybe even adjusted on the fly based on the way that the autopilots and all this stuff works. But if they don't, if it's just like an old Cherokee 140, you need to keep this chart handy and understand exactly like what the temperature is doing to those cables, and this is usually included in the maintenance manuals of the aircraft to help mitigate this in particular risk factor. Okay, so the last component of all this is going to be understanding how to set the control surface travel correct, or at least checking it. At full stops, the control surfaces should only be able to deflect so many degrees, and you'll check that with the propeller protractor. Now, this comes in two different forms. We have digital versions of it now, as well as these old like bubble levels, things like that. Now, you out in the wide world, depending on where you go and who you're working with and what their budget is for tooling, you could get these or you could get the digital ones. Now, ironically, the digital ones are actually a lot cheaper than the old school propeller protractors. Now, granted, the old school propeller protractors are actually a lot more reliable and accurate because they just use basic physics, and it just kind of is what it is. You can't really get too far off, honestly. Whereas the digital ones, you'll have to get them, be a lot more diligent with your calibration with those, because they can throw off. But essentially, all you're really going to do is you're going to put the flight control at a set level of deflection based on the control input in the cockpit, and then you're going to put the propeller protractor on there and make sure that it indicates the right level of deflection.
Now, your flight control travel is largely going to be dictated off of the maintenance manual, but more primarily the TCDS. Every aircraft in their TCDS will tell you, hey, look, the aileron travels from this to this, the elevator travels from that to that, rudder, so on and so forth. So if you ever get lost or confused, you can't find a maintenance manual or whatever, or you want to check and make sure that that aircraft has been rigged properly, the TCDS will tell you, hey, look, this model should be rigged in such and such a way. And that's like a known quantity for every aircraft model that you come across. And so just take the TCDS, do your flight control travel checks per the AMM, so that way it's it's done correctly, and there you have it. And that is how you rig flight controls on an aircraft.